12. Use the limit definition to evaluate. Okay. We're going to go ahead and have delta x approach 0. Now, if we could plug this in, great, but unfortunately, we'd have a division by 0. So what we've got to do is we have to FOIL this out very carefully. Now, delta x has got two things next to it, two symbols. So we could just switch this out for an h right now, okay? And I think that I encourage you guys to do that. But what I want to do, though, is I'm going to keep the delta x, okay? And the reason is I want you to get comfortable just seeing it. But if we swapped it out with the h, which is what we're going to be doing in the next chapter, it's just fine. It means the same thing, okay? All right, so this is what it would look like. I need to FOIL all this out. Now, I'm still taking the limit, actually, as delta x goes to 0. So here we go. Okay, we've got x squared plus 2x delta x plus delta x squared. Okay, now that is foiling this guy. Okay, so you would have just an h there. Okay, but again, I want you to just don't worry about delta h. Like he's going to show up a lot, and I don't want you to be intimidated by him. He's just another variable. Okay. All right. So minus though. Nothing's going on there. That is just going to be x. Then I'm going to do minus delta x because this is just going to distribute there. Okay. Then I'm going to do minus x squared plus x. Okay. All right. Now it's still over delta x. All right. So the way this is going to work out here is something beautiful happens. All right. This guy and this guy always cancel out in situations like this. Okay, it's kind of nice. And then this guy here and here will cancel out. Okay, and then what you would be left with are these delta x's. Okay, now we haven't gotten delta x going to 0 yet. We have not swapped it out, but what we have is we have 2x delta x plus delta x squared minus delta x all over delta x. And guess what they all have in common? A delta x. So we're going to pull a delta x out of each and every one of them. Okay, and so this guy will divide into there, he'll divide into there, and he will divide into there. And what we'll be left with is just a 2x. We will have a delta x there, and then we will have a 1 here, okay, because delta x divided by delta x is just 1, okay. Now, again, we still have not made delta x go to 0 yet, so that limit still is following us along, okay? But now we can do a straight-up substitution. This guy right here goes to 0, okay? We're going to plug it in, and then what you're left with is 2x minus 1, okay? And I know it would have been easier just to use an h, but I wanted you to see the delta x. It's not that big of a deal, but in the beginning, it's just better to use an h. Okay, so for the piecewise function here, use one-sided limits here in the appropriate manner to find the value of the k constant that makes this function continuous. Okay, we've done this before in the other examples, so it looks like we need to have these guys equal to each other. Oh, sorry, my bad. Oh, I said I'm sorry. No rubber bands around here. They're going to equal each other here. Okay, and so what we got to do is we got to find a value of k that will make these guys lined up. Now, two variables, one's got to go, and so we need some other information. Okay, so I see here that the x is -1. Okay, so k -1 squared equals k times -1 plus 5. So this would be k equals -k plus 5. Move the -k over to the other side, so you get a 2k equals 5 divided by 2. So k equals 5 divided by 2, which is 2.5. I'm going to double check it. Okay, there you go. Okay. So yep, it does not say justify, so we're not going to do the whole thing. I can see in the answer key here that they got a thing there. Okay. All right. So now, though, 14 does say use the intermediate value theorem. Okay. We're going to show that this function here, which is a quadratic, has a 0 on the interval 1 to 2. Okay. So, number 1, okay, f of x is continuous. Okay, because it is a polynomial. If you said quadratic, it's the same thing. It's okay. Quadratic is a subset of the polynomials. Okay, so there we go. So it's continuous. So part 2, what we'll do is we're going to go ahead and find out what those values are at the end points of the interval. Okay, so let's do f of 1. F of 1, plug it in. It looks like I'm getting 2 plus 3 is 5. 5, that's negative 3. Okay, cool. And now I need f of 2. Okay, so f of 2, I'm going to write this out because at this time of night I do not trust myself. Okay, that's 8 plus 6 minus 8 is 6. Okay, so I'm getting 6. All right, now 3. Okay, by the EV, and you can write this in many different ways. Okay, let's go since. Since f of 1 is less than 0 and f of 2 is greater than 0, okay, and we already stated that it's continuous, okay, so since that is greater than 0 and that, by the IVT, did I say EVT before? By IVT, there is oh man, you could say there is a C, okay, such that, I don't know if I've ever said it like this though, f of c equals 0, okay, on the interval, I feel like I'm saying this different than usual, on the interval 1 to 2, okay, okay, or you could have said there is a 0 on the interval 1 to 2. Okay. All right, so those are our 3 components there, and that's it. We've used the interval theorem, intermediate value theorem appropriately. Okay. All right, we'll actually stop there.